At the close of the 19th century, science appeared to stand on solid, almost immovable ground. For more than 200 years, the universe had been described with extraordinary success through the language of classical physics. Motion could be predicted with precision, planetary orbits calculated centuries into the future, bridges engineered to withstand enormous forces, and machines designed with confidence that nature would behave exactly as expected. The laws governing matter, energy, and motion seemed not only reliable but complete. Many leading physicists of the time openly believed that the great discoveries were already behind them, and that the future of physics would consist merely of refining measurements to additional decimal places. This sense of completion did not arise from arrogance alone. It was supported by remarkable achievements. Newton's mechanics had explained motion on Earth and in the heavens with a single framework. Maxwell's equations had unified electricity, magnetism, and light into one elegant theory, revealing light itself as an electromagnetic wave. Thermodynamics had clarified how heat, work, and energy interacted, introducing concepts such as entropy and the irreversible flow of time. Together, these theories formed a powerful structure that seemed capable of explaining all physical phenomena. Within this framework, nature was assumed to be continuous and deterministic. Energy could vary smoothly, without jumps or gaps. Matter moved along well-defined trajectories. If one knew the initial conditions of a system with sufficient precision, its future behavior could, in principle, be predicted exactly. This worldview painted the universe as a perfectly functioning clockwork mechanism, governed by precise mathematical laws. Human ignorance was seen as the only barrier to complete understanding. Yet even as this confidence grew, small cracks began to appear. Certain experimental results stubbornly refused to align with theoretical predictions. At first, these discrepancies were treated as minor anomalies, expected to vanish with better instruments or more refined equations. No one imagined they pointed to a deeper problem. However, as experimental techniques improved, the inconsistencies not only persisted but became impossible to ignore. One of the most troubling challenges arose from the study of heat and radiation. When objects are heated, they emit electromagnetic radiation, a phenomenon observed daily in glowing metal, flames, and the sun itself. Physicists sought to describe this radiation quantitatively, believing it should follow directly from known laws of electromagnetism and thermodynamics. Laboratories across Europe began measuring the intensity of radiation emitted at different wavelengths and temperatures with unprecedented accuracy. The results were precise, repeatable, and deeply unsettling. Classical theory predicted that as the wavelength of radiation decreased, the energy emitted should increase without limit. According to the equations, hot objects should release an infinite amount of energy at very short wavelengths. This prediction was not just slightly wrong, it was physically impossible. Experiments showed that radiation peaked at a certain frequency and then rapidly declined, avoiding the catastrophic divergence predicted by theory. This conflict exposed a fundamental weakness in classical physics. The equations that worked flawlessly for mechanical systems and electromagnetic waves failed spectacularly when applied to microscopic energy exchanges. Theories that had explained so much suddenly appeared fragile. The ultraviolet catastrophe, as it later came to be called, was not merely a technical error, but a warning sign that something was deeply wrong with the underlying assumptions about nature. At the same time, other puzzles were emerging. The stability of atoms could not be explained. According to classical electromagnetism, electrons orbiting a nucleus should continuously emit radiation, lose energy, and spiral inward until the atom collapsed. Yet atoms were stable, matter existed, chemistry functioned, life persisted. Classical physics offered no explanation for this contradiction. Spectral lines presented another mystery. When elements were heated or energized, they emitted light at specific, discrete frequencies rather than a continuous spectrum. These sharp lines acted like fingerprints for each element, but classical theory could not account for why only certain frequencies appeared. The data was clear, but theory lagged far behind. Despite these growing problems, many physicists remained confident that classical principles would ultimately prevail. The dominant belief was that a few clever adjustments would restore harmony between theory and experiment. No one suspected that the very foundations of physics would need to be re-examined. The notion that energy itself might not be continuous was considered unthinkable. Continuity was not merely an assumption, it was a philosophical cornerstone inherited from centuries of scientific thought. This intellectual climate created an atmosphere of tension. On the surface, physics seemed complete, but beneath that surface lay unanswered questions that refused to disappear. Young physicists were often advised to pursue other fields, as physics was believed to offer little room for groundbreaking discovery. Ironically, this perceived stagnation masked the fact that physics was on the brink of its most radical transformation. The crisis of classical physics was not announced with drama or fanfare. It unfolded quietly through failed calculations, mismatched curves, and equations that produced nonsensical infinities. These failures forced an uncomfortable realization. The tools used to understand the macroscopic world might not apply to the microscopic one. Nature, it seemed, was hiding secrets that classical intuition could not penetrate. What made this moment so significant was not just the presence of unsolved problems, but the realization that they could not be resolved within the existing framework. The contradictions were not isolated, they were interconnected, pointing toward a deeper breakdown in understanding. The very assumptions about how energy flows, how matter interacts with radiation, and how physical systems behave at small scales were being called into question. This period marked a turning point in the history of science. It was the moment when certainty gave way to doubt, when confidence was replaced by curiosity and unease. The crisis of classical physics did not signal the failure of science, but rather its resilience. Faced with contradictions, science did what it always does at its best: it questioned itself. Out of this tension would emerge new ideas that challenged everything physicists thought they knew. But at this stage, those ideas had not yet taken form. All that existed was a growing awareness that the old answers were no longer sufficient. The universe was whispering that its rules were stranger than anyone had imagined, and that to understand it, science would have to abandon some of its most cherished beliefs. This was the world into which Max Planck introduced his revolutionary assumption, not as an act of rebellion, but as a response to a crisis that classical physics could no longer ignore. As the crisis deepened, the confidence that once defined classical physics slowly transformed into unease. The mathematical elegance that had guided generations of scientists now produced contradictions that could not be dismissed as experimental error. What made the situation especially troubling was that the failures were not occurring at the fringes of physics, but at its very core. Heat, light, and matter were fundamental aspects of nature, and yet the theories designed to explain them were collapsing under scrutiny. Physicists began to realize that the problem was not with isolated equations, but with the assumptions beneath them. Classical physics treated energy as a smooth, infinitely divisible quantity, much like water flowing through a pipe. This idea had worked well for large-scale systems, but when applied to microscopic interactions, it produced absurd predictions. The equations did exactly what they were designed to do. It was reality that refused to cooperate. The growing mismatch between theory and experiment placed science in an uncomfortable position. Experimentalists could measure radiation curves with astonishing accuracy, but theorists could not explain them without invoking infinities. In physics, an infinity is not just an inconvenient number, it is a sign that a theory has gone beyond its domain of validity. Each appearance of infinity was a silent confession that something fundamental was missing. Attempts to resolve these issues within the classical framework grew increasingly desperate. New mathematical tricks were introduced, correction terms added, and assumptions modified, but none of these efforts produced a stable, universal solution. Every fix seemed to solve one problem only to create another. The deeper physicists dug, the clearer it became that the crisis was not superficial. This realization challenged more than equations, it challenged identity. For centuries, physics had been regarded as the ultimate model of rational certainty. To admit that its foundations were incomplete felt, to many, like intellectual defeat. Yet evidence left no room for denial. The universe was behaving in ways that classical physics simply could not describe. At the heart of this tension was a philosophical struggle. Classical physics was deeply rooted in determinism, the belief that nature follows precise rules that fully determine outcomes. If energy and motion were continuous, then every effect had a clear, traceable cause. This view aligned comfortably with human intuition and the mechanical worldview shaped by everyday experience. But the experimental data, emerging at the turn of the century, hinted at a different reality, one where nature might impose limits on how energy could be exchanged. This idea was deeply unsettling. It implied that continuity, one of the most sacred principles in physics, might not be universal. The possibility that nature operated in discrete steps rather than smooth flows threatened to dismantle centuries of scientific tradition. What made this crisis particularly difficult was that it could not be visualized easily. Classical physics thrived on mental pictures, particles moving along paths, waves spreading through space, forces acting continuously. The new problems offered no such clarity. They suggested behaviors that resisted visualization, existing beyond the reach of common sense. Young physicists entering the field during this time found themselves caught between admiration for classical achievements and frustration at their limitations. Some clung to the hope that a hidden variable or undiscovered mechanism would restore continuity. Others sensed that a more radical departure was inevitable, even if they could not yet articulate what it would look like. The crisis also revealed an important truth about science itself. Scientific progress is not a smooth accumulation of knowledge, but a series of ruptures. Periods of apparent stability can conceal unresolved contradictions that, once exposed, force dramatic change. The end of the 19th century was one such moment, a quiet threshold between two intellectual worlds. As confidence in classical physics wavered, the scientific community became increasingly open, if reluctantly, to unconventional ideas. The rigid boundaries that once defined acceptable explanations began to loosen. It was within this atmosphere of uncertainty that new thinking could finally emerge, not from bold speculation alone, but from the necessity imposed by experimental facts. The crisis did not invalidate classical physics, it redefined its limits. Newton's laws still described planets and projectiles, Maxwell's equations still governed radio waves and optics, and thermodynamics still ruled engines and heat flow. But these theories were no longer seen as universal truths. They were approximations, valid within certain domains, but incomplete at the smallest scales. This shift in perspective was revolutionary. It introduced the idea that physical laws might depend on scale, that the universe could follow different rules, depending on how closely one looked. Such a notion was foreign to the classical mindset, which sought universal principles applicable everywhere and always. The inability of classical physics to explain microscopic phenomena marked the beginning of a new scientific humility. Physicists were forced to accept that intuition, shaped by everyday experience, might be a poor guide to the fundamental nature of reality. The universe was not obligated to make sense in human terms. Out of this intellectual tension arose a willingness to consider ideas that would previously have been dismissed as absurd. It was no longer enough for a theory to feel reasonable, it had to match observation, even if it defied common sense. This shift in attitude would prove crucial for the breakthroughs that followed. The crisis of classical physics, therefore, was not merely a technical failure, but a transformation in how science understood itself. It marked the end of the illusion that nature could be fully captured by smooth, continuous laws. It prepared the scientific mind for a deeper, stranger reality, one where certainty would be replaced by probability and continuity by discreteness. By the time Max Planck introduced his radical assumption about energy quanta, the ground had already been softened by years of unresolved contradictions. His idea did not emerge in isolation. It was the inevitable response to a framework that could no longer sustain itself. The shock of his proposal would soon ripple through physics, but it was the crisis of classical theory that made such a shock possible. This moment stands as a reminder that scientific revolutions are rarely driven by ambition alone. They are born from necessity, from the refusal of nature to conform to expectation. When the old answers fail, science does not collapse, it evolves. And in that evolution, our understanding of reality is forever changed. When physicists at the end of the 19th century turned their attention to the nature of heat and light, they believed they were entering familiar territory. Heat had already been formalized through thermodynamics, and light had been successfully described as an electromagnetic wave by Maxwell's equations. The assumption was simple and reassuring. Combine these powerful theories, and the behavior of thermal radiation would naturally follow. What they encountered instead was one of the most stubborn and consequential problems in the history of science. Every object with a temperature above absolute zero emits electromagnetic radiation. This radiation depends only on the object's temperature and not on its shape, size, or material when idealized under certain conditions. To study this phenomenon precisely, physicists imagined an ideal object known as a blackbody, a system that absorbs all incoming radiation and emits energy in a perfectly characteristic way. Blackbody radiation was not an abstract curiosity, it was central to understanding furnaces, stars, and even the glow of everyday objects. Experiments measuring blackbody radiation became increasingly accurate thanks to advances in instrumentation. Scientists could plot curves showing how much energy an object emitted at different wavelengths for a given temperature. These curves had a clear structure at low frequencies. Radiation increased with frequency, it reached a peak, then it declined sharply at higher frequencies. The pattern was consistent and reproducible across laboratories and countries. The challenge was not experimental but theoretical. Classical physics attempted to derive these curves using established principles. According to classical electromagnetism, radiation inside a cavity could be treated as standing electromagnetic waves. Thermodynamics then dictated how energy should be distributed among these waves. When the mathematics was carried out, the result was deeply disturbing. The equations predicted that the energy emitted at higher frequencies should grow without bound. As the wavelength approached zero, the predicted energy approached infinity. This was not merely an incorrect prediction, it was a physical impossibility. No object could emit infinite energy. The theory implied that even moderately warm objects would release catastrophic amounts of ultraviolet radiation, something clearly contradicted by observation. This discrepancy became known as the ultraviolet catastrophe, though at the time it was simply seen as an embarrassing failure. The catastrophe was not subtle. Theoretical curves diverged wildly from experimental data precisely in the region where measurements were most reliable. The more carefully physicists measured radiation at short wavelengths, the more obvious the breakdown of classical theory became. What made the problem especially troubling was that it arose directly from well-established principles. There was no obvious mistake in the mathematics. The logic was sound, the equations were consistent, and yet the conclusions were absurd. This meant the problem lay deeper than a calculation error. It lay in the assumptions about how energy behaved. Classical physics assumed that energy could be divided endlessly into smaller and smaller amounts. An electromagnetic wave could carry arbitrarily small energy, and energy could be exchanged continuously between matter and radiation. This assumption had never been questioned because it worked so well in everyday situations. But blackbody radiation exposed its limits. Physicists attempted numerous fixes. Some tried modifying boundary conditions, others introduced ad hoc correction factors, and still others proposed new interaction mechanisms between matter and radiation. None of these approaches provided a universal solution. They either worked only in limited regions of the spectrum or violated other well-tested laws of physics. The failure was deeply unsettling because blackbody radiation was not an exotic phenomenon, it was ubiquitous. The sun's light, the glow of heated metal, and even the cosmic background radiation that fills the universe are all forms of thermal radiation. If classical physics could not explain something so fundamental, its claim to completeness was seriously undermined. The problem also revealed a growing divide between theory and experiment. Experimental physicists trusted their data, the measurements were precise and consistent. Theoretical physicists trusted their equations, they were derived from principles that had proven successful countless times before. When these two pillars of science disagreed so dramatically, there was no easy resolution. What made the situation worse was that partial successes masked the full extent of the problem. At low frequencies, classical predictions matched experiments reasonably well. This gave the illusion that only minor adjustments were needed. But at high frequencies, the theory collapsed completely. The mismatch was not gradual but catastrophic, suggesting that classical physics was fundamentally incapable of describing the phenomenon as a whole. This selective success was dangerous because it delayed recognition of the true nature of the crisis. Many physicists believed that a clever mathematical refinement would eventually bridge the gap. Few suspected that the solution would require abandoning the idea of continuous energy altogether. The blackbody radiation problem forced physicists to confront an uncomfortable truth: theories are not validated by elegance or past success alone. They must work in every domain they claim to describe. Classical physics had overextended itself, applying macroscopic intuition to microscopic processes where it no longer applied. As years passed without a satisfactory solution, the problem gained symbolic importance. It became a benchmark for any new theory of radiation. Any proposed framework had to reproduce the observed blackbody spectrum exactly, not approximately. The precision of the data left no room for vague explanations or qualitative arguments. The crisis also reshaped how physicists thought about modeling nature. It highlighted the danger of assuming that familiar concepts remain valid at all scales. Heat and light, once thought to be fully understood, turned out to conceal a deeper layer of complexity that classical theories could not penetrate. By the time Max Planck began working seriously on the problem, it was clear that conventional approaches had failed. Planck was not motivated by a desire to overturn physics, but by the urgent need to explain the data. The blackbody radiation curves were undeniable facts, and any theory that contradicted them was simply wrong. This problem set the stage for a conceptual leap that no one anticipated. It showed that the crisis of classical physics was not abstract or philosophical, but grounded in concrete experimental evidence. Nature itself was signaling that its behavior at small scales followed rules that had yet to be discovered. The blackbody radiation problem stands as a powerful example of how science advances. It demonstrates that progress often begins not with bold speculation, but with careful measurement revealing contradictions that cannot be ignored. When theory fails repeatedly in the face of data, a new way of thinking becomes inevitable. What made this problem historically decisive was that it could not be postponed or sidestepped. It affected astronomy, thermodynamics, optics, and emerging technologies. Its resolution would determine whether physics could continue as a coherent discipline or fragment under the weight of its own inconsistencies. Thus, blackbody radiation was not just an unsolved puzzle, it was a challenge to the very framework through which physicists understood the world. It forced science to the edge of its classical foundations, preparing the ground for an idea so radical that even its creator initially resisted its implications. As the implications of the blackbody radiation problem sank in, the scientific community found itself confronting a dilemma that went far beyond a single failed prediction. What initially appeared to be a narrow technical issue was now recognized as a symptom of a much deeper theoretical breakdown. The failure was not isolated to one equation or one experimental setup. It was woven into the very fabric of classical reasoning about energy and matter. One of the most unsettling aspects of the problem was how unavoidable it was. Blackbody radiation could not be dismissed as an artificial construct. Cavities emitting radiation, heated solids, glowing stars, and furnaces all exhibited the same fundamental behavior. The phenomenon was universal. Any theory claiming to describe nature had to explain it, not approximately but exactly. Precision measurements had become so reliable that even small deviations between theory and experiment were unacceptable. Physicists gradually realized that the ultraviolet catastrophe was not merely an embarrassment but a diagnostic tool. It exposed the precise point at which classical physics stopped working. At low frequencies, classical predictions aligned well with observations. At high frequencies, they failed completely. This sharp boundary suggested that classical ideas were not wrong everywhere, but wrong in a specific regime. Understanding why they failed there became the central question. The deeper scientists looked, the more they recognized that the problem lay in how energy was being counted. Classical physics assumed that energy could be distributed among electromagnetic modes in infinitely small amounts. In mathematical terms, each mode was allowed to carry any energy value, no matter how tiny. When combined with the assumption that there were infinitely many such modes at high frequencies, the result was an infinite total energy. The mathematics followed inevitably from the assumptions. This realization was disturbing because it implied that the catastrophe was not a flaw in calculation, but a logical consequence of deeply held beliefs. The idea that nature allowed infinite divisibility of energy had never been tested directly at microscopic scales. It was simply assumed, inherited from centuries of thinking shaped by macroscopic experience. Blackbody radiation was now exposing that assumption as questionable. The crisis also highlighted a growing divide between physical intuition and experimental reality. Classical intuition imagined radiation as waves smoothly oscillating through space, carrying energy in a continuous flow. But experiments suggested that something more constrained was happening. Energy exchange appeared to be limited in ways that classical waves could not explain. As debates intensified, some physicists attempted to reinterpret the data rather than abandon classical principles. They argued that the failure might lie in how matter interacted with radiation, not in the nature of energy itself. Perhaps atoms had unknown properties that suppressed high-frequency emissions. Perhaps energy transfer mechanisms were more complex than previously thought. These ideas, however, lacked predictive power and could not reproduce the observed radiation curves consistently. Others proposed that classical physics might still be correct, but incomplete. They suggested that additional forces or hidden variables might exist, waiting to be discovered. This approach preserved continuity and determinism, but it offered no concrete solutions. Without experimental evidence for such hidden mechanisms, these proposals remained speculative. The persistence of the problem forced physicists into an uncomfortable position. For the first time in generations, they had to accept that some of their most trusted concepts might not be universally valid. The assumption that nature behaved smoothly at all scales was no longer defensible. The data was relentless, and it demanded a response. This period marked a subtle but profound shift in scientific thinking. The goal was no longer to protect classical theory at all costs, but to follow evidence wherever it led. This shift did not happen overnight. It was gradual, marked by resistance, debate, and uncertainty. Yet it created the intellectual space necessary for new ideas to be considered seriously. The blackbody radiation problem also influenced how physicists viewed the role of mathematics in science. Classical physics had enjoyed a long period where mathematical elegance and physical truth seemed inseparable. Equations that were beautiful often turned out to be correct. In the face of the ultraviolet catastrophe, however, elegant mathematics produced nonsensical results. This forced a reevaluation of the relationship between mathematical form and physical meaning. It became clear that equations alone could not guarantee truth. They had to be grounded in assumptions that accurately reflected nature. If those assumptions were wrong, even the most sophisticated mathematics would lead astray. This realization encouraged greater scrutiny of foundational concepts, not just technical details. The unresolved nature of the blackbody problem also had psychological effects on the scientific community. Young researchers sensed that something extraordinary was happening. Established authorities, once confident, now expressed uncertainty. Textbooks quietly acknowledged unresolved issues. Lectures ended with unanswered questions rather than firm conclusions. Physics, once seen as complete, was becoming a field of open mysteries. This atmosphere of uncertainty was fertile ground for innovation. When a discipline acknowledges its limits, it becomes receptive to radical ideas. The blackbody radiation problem did not dictate the solution, but it defined the constraints any solution had to meet. It demanded a theory that preserved agreement with experiment across all frequencies without producing infinities. The problem also underscored the importance of empirical discipline. No matter how strongly physicists believed in continuity, determinism, or classical waves, those beliefs had to yield to measurement. The radiation curves were facts. They did not negotiate. Any acceptable theory had to bend to them, not the other way around. As the 19th century gave way to the 20th, it became increasingly clear that a conceptual leap was unavoidable. Incremental modifications had failed. The structure of classical physics, though powerful, was too rigid to accommodate the observed behavior of radiation. Something fundamentally new was required, something that redefined how energy itself was understood. What made this moment so remarkable was that the crisis arose not from exotic experiments but from careful, methodical study of ordinary phenomena. There was nothing mystical about a heated cavity emitting light. And yet, this simple system exposed the limits of an entire worldview. It revealed that even the most familiar aspects of nature could harbor profound secrets. The blackbody radiation problem thus became a turning point. It demonstrated that scientific revolutions do not always begin with bold predictions or dramatic discoveries. Sometimes they begin with a refusal of nature to cooperate with existing ideas. When that refusal persists, it forces a transformation. By the time Max Planck introduced his solution, the scientific community was ready, even if reluctantly, to accept something radical. The failure to solve blackbody radiation within classical physics had exhausted all conventional options. The stage was set for an idea that would redefine energy, challenge continuity, and reshape physics forever. In this sense, the blackbody radiation problem was not just a technical challenge, but a philosophical one. It questioned whether human intuition, shaped by the macroscopic world, could ever fully grasp the microscopic rules of nature. It suggested that reality might be structured in ways that defy smoothness, predictability, and classical logic. This realization marked the true end of the classical era, not because classical physics stopped working, but because it was revealed to be incomplete. Its success remained undeniable, but its authority was no longer absolute. The universe had shown that it operated under deeper principles, waiting to be uncovered. The problem of blackbody radiation, therefore, stands as one of the most important episodes in scientific history. It represents the moment when physics was forced to confront its own limitations, and in doing so, opened the door to a new understanding of reality. The shock it delivered was not sudden but cumulative, building through years of failed explanations until a radical idea became not just acceptable but necessary. Out of this necessity would emerge a concept so strange and counterintuitive that it would initially be treated as a mere mathematical trick. Yet that concept would ultimately become the foundation of modern physics, transforming our understanding of light, matter, and the very structure of the universe. At the moment when Max Planck confronted the blackbody radiation problem, he was not searching for a revolution. In fact, his intellectual temperament was the opposite of radical. Planck was deeply committed to the classical worldview, particularly to thermodynamics, which he regarded as one of the most solid achievements of physics. He believed strongly in absolute laws of nature and was skeptical of statistical or probabilistic interpretations. His goal was not to invent a new physics, but to save the old one from an embarrassing failure. Planck approached the radiation problem as a mathematical challenge rather than a conceptual one. He trusted that the correct formula existed and that it would reconcile experimental data with established principles. His initial work focused on deriving an equation that would fit the observed radiation curves exactly. He was less concerned with physical interpretation and more focused on achieving mathematical agreement with experimental results. To Planck, a correct formula was evidence of an underlying physical truth, even if that truth was not yet fully understood. The data from experiments on blackbody radiation were precise and unforgiving. The curves showing intensity versus frequency were smooth, well-defined, and consistent across different experimental setups. Planck knew that any successful theory had to reproduce these curves perfectly. Approximate agreement was not enough. The slightest deviation would expose the theory as inadequate. This demand for exactness narrowed the range of possible solutions dramatically. Planck began by examining existing theoretical expressions. Two partial formulas already existed, each working well in a limited range of frequencies. One matched experimental data at low frequencies, while the other performed well at high frequencies. Neither was correct across the entire spectrum. Planck's task became one of unification, to find a single expression that smoothly connected these two regimes without producing infinities or contradictions. Through mathematical ingenuity, Planck discovered a formula that fit the data exactly. This alone would have been a triumph. But when he tried to justify the formula using classical assumptions, he failed. The mathematics worked, but the physical reasoning did not. The classical derivations inevitably led back to the ultraviolet catastrophe. Something essential was missing. It was at this point that Planck made his most extraordinary move. In an act he later described as one of desperation, he introduced a new assumption into his calculations. He proposed that the energy exchanged between matter and radiation did not vary continuously, but occurred in discrete amounts. These amounts were proportional to the frequency of radiation, connected by a new fundamental constant. This assumption was not derived from observation of particles or waves. It was not motivated by experimental evidence of discreteness in energy. It was introduced solely to make the mathematics work. Planck treated energy as if it could only take on specific values, integer multiples of a basic unit. This step allowed him to count the possible ways energy could be distributed, avoiding the infinities that plagued classical theory. To Planck, this was a formal trick, not a statement about reality. He did not claim that energy was truly granular in nature. Instead, he viewed the assumption as a convenient mathematical device that happened to produce the correct result. He believed that a deeper classical explanation would eventually emerge, one that would remove the need for such an artificial restriction. What made this assumption so radical was not just its novelty, but what it denied. Classical physics was built on continuity. Energy flowed smoothly. Changes occurred gradually. By introducing discrete energy elements, Planck violated one of the most fundamental principles of classical thought. He effectively placed a limit on how small an energy exchange could be. The constant that appeared in his formula, now known as Planck's constant, was astonishingly small. Its numerical value suggested that quantization effects would only become noticeable at extremely small scales. This explained why classical physics had worked so well for everyday phenomena. The granularity of energy was hidden from macroscopic experience, emerging only in microscopic interactions. Planck's introduction of this constant was not accompanied by philosophical enthusiasm. He did not celebrate the breakdown of continuity. On the contrary, he was uneasy about it. He hoped that the quantization would eventually be understood as an approximation or an artifact of the calculation. For years, he resisted the idea that it represented a fundamental feature of nature. Nevertheless, the success of the formula could not be ignored. It matched experimental data with stunning accuracy across all frequencies and temperatures. Where classical theories failed catastrophically, Planck's expression worked flawlessly. This empirical success gave the assumption a legitimacy that no philosophical discomfort could undermine. The mathematical framework Planck used involved counting the number of ways energy could be distributed among oscillators. By restricting energy to discrete values, the counting became finite and well-defined. This statistical approach was unfamiliar and uncomfortable for someone who valued deterministic laws. Yet it proved indispensable. Planck's assumption quietly introduced a new way of thinking about physical systems. Instead of treating energy as a continuous variable, it became something that could only change in jumps. These jumps were not arbitrary, but governed by precise mathematical rules. Energy exchange became quantized, constrained by frequency and a universal constant. The radical nature of this idea was not immediately apparent to the wider scientific community. Many physicists saw Planck's work as a clever mathematical solution to a specific problem, not as a foundational shift. Even Planck himself presented it cautiously, avoiding bold claims about its physical meaning. Yet embedded within his assumption was a profound implication: nature might be fundamentally discrete at its deepest level. This idea stood in stark contrast to the smooth, continuous universe envisioned by classical physics. It suggested that there were limits to divisibility, that not everything could be broken down indefinitely. The reluctance to accept this implication delayed its full impact. For several years, Planck's quantization was treated as a technical detail rather than a revolutionary insight. It was only when other physicists began applying the idea to different phenomena that its true significance became clear. What makes Planck's assumption especially remarkable is how little confidence he had in it at first. Unlike many revolutionary ideas, it was not born from bold speculation or philosophical conviction. It emerged from necessity, from the refusal of experimental data to conform to established theory. Planck followed the mathematics where it led, even when it took him somewhere he did not want to go. This episode illustrates an important feature of scientific progress. Revolutionary ideas are not always recognized as such at the moment of their birth. Sometimes they appear as modest adjustments, technical fixes, or mathematical conveniences. Their deeper meaning only becomes visible in hindsight when their consequences unfold. Planck's assumption did not immediately overthrow classical physics. Instead, it introduced a fault line that would slowly widen over the coming decades. As more phenomena were explained using quantization, the idea gained credibility. What began as a reluctant assumption became a cornerstone of a new physics. The introduction of elementary energy quanta marked a turning point in scientific thought. It showed that even the most deeply ingrained assumptions could be questioned when confronted with evidence. It also demonstrated that mathematics, when guided by experiment, could reveal truths that intuition alone could not grasp. In retrospect, Planck's radical assumption stands as one of the most important moments in the history of science. It was the first clear break from classical continuity, the first acknowledgement that nature might operate according to rules fundamentally different from those humans had imagined. Yet at the time, it was presented with hesitation, wrapped in caution, and burdened by doubt. That hesitation makes the achievement even more striking. Planck did not seek to shock science, but his assumption did exactly that. It planted the seed of quantum theory, a seed that would soon grow beyond his control, reshaping physics, chemistry, and technology in ways no one could have predicted. What began as a mathematical compromise became a window into the true structure of reality. And although Planck himself struggled to accept the implications, his willingness to follow evidence over belief changed science forever. As Planck reflected on the implications of his assumption, a quiet tension followed his success. On the surface, the problem of blackbody radiation appeared solved. The experimental curves matched theory with remarkable precision, and the embarrassing infinities had disappeared. Yet beneath this technical triumph lay a conceptual unease that Planck could not ignore. He had introduced an idea that did not sit comfortably within the intellectual structure he trusted most. Planck's discomfort stemmed from the nature of the assumption itself. Classical physics did not merely prefer continuity, it depended on it. The smooth flow of energy was woven into mechanics, electromagnetism, and thermodynamics alike. By allowing energy to exist only in discrete amounts, Planck had implicitly suggested that nature imposed limits where none had been imagined before. This was not a small modification. It was a fundamental restriction on how physical processes could occur. Rather than embracing this implication, Planck initially treated quantization as a mathematical convenience. He believed that the discreteness applied only to the interaction between matter and radiation, not to energy itself as an intrinsic property. In his view, the quantized elements were bookkeeping tools, introduced to make statistical calculations manageable. He hoped that future work would reinterpret the result in a way that restored continuity at a deeper level. This cautious interpretation influenced how Planck presented his work. He avoided dramatic language and refrained from making philosophical claims. His publications focused on derivations, constants, and formulas, not on metaphysical consequences. As a result, many contemporaries failed to grasp how radical the idea truly was. It was seen as a clever solution to a narrow problem rather than a challenge to the foundations of physics. The scientific community's reaction mirrored Planck's own ambivalence. While his formula was widely accepted for its accuracy, the underlying assumption was often ignored or downplayed. Physicists used the equation without fully committing to its implications. The success of the result allowed many to postpone deeper questions about what quantization meant for the nature of reality. Yet the seed had been planted. Even if treated cautiously, the idea of discrete energy units had entered scientific discourse. Once introduced, it could not be undone. Other physicists began to notice that the same assumption could illuminate problems far beyond blackbody radiation. The notion that energy exchange occurred in fixed amounts began to appear less artificial and more suggestive of a deeper principle. The true turning point came when the assumption was taken seriously by others, not as a mathematical trick but as a physical statement. When Albert Einstein applied quantization to light itself, proposing that electromagnetic radiation behaved as if it were composed of discrete packets, the meaning of Planck's constant changed dramatically. What had been a formal device now appeared to describe the structure of nature. This development retroactively transformed Planck's work. The constant he had introduced reluctantly became a fundamental boundary in physics, defining the scale at which classical concepts break down. The discreteness he had hoped to explain away became unavoidable. Energy was not merely behaving as if it were quantized, it was quantized. The realization forced a reinterpretation of Planck's original assumption. It was no longer sufficient to view it as a statistical artifact. Instead, it was understood as the first glimpse into a new regime of physics, one where familiar ideas such as continuity, determinism, and precise trajectories no longer applied. The discomfort Planck felt was not a sign of error, but a signal that something profoundly new had been uncovered. What makes this episode especially striking is how modest its beginnings were. There was no dramatic proclamation, no immediate rejection of classical theory. The revolution began quietly, hidden inside a constant and an equation. Only later did its implications unfold, reshaping entire fields of science. Planck's reluctance also highlights an important truth about scientific discovery. The originator of an idea is not always the one who fully understands its consequences. Planck opened the door to quantum theory, but others would walk through it, pushing the concept far beyond its initial scope. This does not diminish his contribution, it underscores its depth. As quantization was applied to atoms, electrons, and radiation, the assumption gained a coherence it had initially lacked. What seemed arbitrary in isolation became natural in a broader framework. The discrete energy levels of atoms, the emission and absorption of photons, and the stability of matter all pointed toward the same underlying principle. Planck's assumption was no longer an isolated fix, it was the foundation of a new understanding. In hindsight, the hesitation that accompanied Planck's work makes it more credible, not less. He did not impose his personal beliefs onto nature. He allowed experimental evidence to guide him, even when it led to conclusions he found uncomfortable. This intellectual honesty is what allowed the discovery to stand the test of time. The introduction of elementary quanta marked the moment when physics crossed a boundary it did not yet recognize. The classical worldview was still intact on the surface, but a fault line had formed beneath it. With each new application of quantization, that fault line widened, eventually leading to the full development of quantum mechanics. Planck's assumption also altered the relationship between theory and experiment. It demonstrated that experimental facts could force theory into forms that intuition resisted. The role of theory was no longer to preserve familiar concepts, but to accommodate reality even when reality behaved in unexpected ways. This shift had lasting consequences. It prepared physicists to accept ideas that would later seem even more disturbing, such as wave-particle duality, uncertainty, and probability as fundamental features of nature. Without Planck's reluctant step, these later developments might have been impossible. The shock to science, therefore, did not come all at once. It unfolded gradually, as the implications of Planck's assumption became unavoidable. What began as a desperate mathematical choice became the cornerstone of a new physics, one that would challenge not only equations, but the way humans understand the universe itself. In this sense, Planck's radical assumption stands as a reminder that the deepest transformations in science often begin quietly. They arise not from bold declarations, but from careful attention to evidence and a willingness to follow it wherever it leads. Even when the destination is unfamiliar, unsettling, and profoundly transformative, the moment Planck's assumption began to be taken seriously, a quiet but profound transformation occurred in the way science understood energy itself. For centuries, energy had been treated as a smooth, endlessly divisible quantity. Whether describing the motion of planets, the flow of heat, or the propagation of waves, physicists assumed that energy could change by arbitrarily small amounts. This assumption felt natural because it aligned perfectly with everyday experience. You can heat water gradually, dim a light slowly, or reduce speed continuously. Nothing in the macroscopic world suggests that energy arrives in jumps. Planck's work challenged this deeply ingrained belief. By proposing that energy exchange occurs in discrete units proportional to frequency, he introduced the idea that energy is not continuous at the most fundamental level. This was not merely a technical adjustment, it was a conceptual break with centuries of physical thought. It suggested that there exists a smallest possible unit of action, below which energy cannot be subdivided. Nature, according to this idea, operates with built-in granularity. At first, this notion was difficult to accept because it could not be directly observed. The quantum of energy was extraordinarily small. In everyday phenomena, the energy involved is so large compared to this unit that discreteness becomes invisible. Energy appears smooth not because it truly is, but because the steps are too tiny to detect. This explained why classical physics worked so well for so long. It was not wrong, it was incomplete, describing an averaged reality rather than the underlying structure. The birth of the quantum marked the first time physics acknowledged that continuity might be an illusion. Energy was no longer a flowing substance, but something that could only be transferred in fixed amounts. This idea immediately resolved the contradictions seen in blackbody radiation. By limiting how energy could be distributed, the infinite predictions vanished. The universe, it seemed, enforced rules that prevented physical absurdities. What made this realization especially powerful was its universality. The quantization was not tied to a specific material system or experimental setup. It depended only on frequency and a fundamental constant. This suggested that quantization was not an accidental feature of blackbody radiation, but a property of nature itself. Energy exchanges everywhere might be governed by the same rule. Once this door was opened, the implications spread rapidly. If energy was quantized, then the processes involving light, heat, and matter could not be described fully by smooth equations alone. Transitions between states would involve jumps rather than gradual changes. This forced physicists to rethink how systems evolved over time at microscopic scales. The idea also introduced a new kind of limit into physics. Classical laws allowed infinite divisibility, but quantization imposed boundaries. Just as atoms set a limit to how matter can be divided, quanta set a limit to how energy can be exchanged. This parallel was striking. Matter, once thought continuous, had already been revealed to be atomic. Now energy followed a similar pattern. Reality appeared to be built from discrete elements rather than continuous substances. Initially, this parallel was not widely appreciated. Many physicists still hoped that quantization was a temporary mathematical convenience. But as the idea was applied to other phenomena, it gained coherence and explanatory power. The emission and absorption of light by atoms, the stability of matter, and the discrete spectral lines observed in experiments all found natural explanations once energy quantization was accepted. The concept also changed how causality was understood. In classical physics, changes occurred smoothly as forces acted continuously. With quantization, change became step-like. Systems remained in stable states until a quantum of energy was absorbed or released, triggering a transition. This introduced a new kind of behavior that had no classical analog. Importantly, the birth of the quantum did not eliminate classical physics. Instead, it placed it within a broader framework. At large scales, where countless quanta are involved, their discrete nature averages out, producing the smooth behavior described by classical laws. This insight revealed classical physics as an approximation valid under specific conditions, rather than a universal truth. The recognition that energy is not continuous also reshaped scientific humility. It demonstrated that human intuition, shaped by macroscopic experience, is not a reliable guide to fundamental reality. Nature does not organize itself to match human expectations. It follows its own rules, even when those rules appear strange or counterintuitive. Perhaps most importantly, the birth of the quantum introduced a new standard for physical explanation. It showed that limiting assumptions, once considered weaknesses, could actually reflect deeper truths. By accepting limits on divisibility, physics gained coherence, consistency, and predictive power. What began as a reluctant assumption became a defining principle of modern science. The realization that energy is quantized marked the moment when the classical worldview quietly gave way to a new understanding of nature. It was the first clear signal that the universe at its deepest level is structured, discrete, and governed by principles far removed from everyday experience. This shift did not announce itself with dramatic language or immediate consensus. It unfolded gradually as evidence accumulated and implications became unavoidable. But once the quantum was born, science could never return to the idea of a fully continuous universe. A boundary had been crossed, and beyond it lay a reality more subtle, more constrained, and far more profound than anyone had previously imagined. When Planck introduced the idea of quantized energy, the reaction from the scientific community was far from immediate acceptance. Instead of excitement, the prevailing response was hesitation, skepticism, and in many cases quiet dismissal. Physics at the turn of the 20th century was deeply rooted in tradition, and traditions do not collapse easily. The idea that energy, one of the most fundamental quantities in nature, could exist only in discrete packets, seemed to undermine the coherence of everything scientists believed they understood. Many physicists regarded Planck's assumption as a mathematical anomaly rather than a physical truth. The formula worked, but that did not mean its underlying interpretation was correct. Classical physics had taught generations of scientists to trust continuity, determinism, and smooth mathematical descriptions of nature. To accept quantization was to accept that nature behaved in jumps, an idea that felt crude and unscientific to minds trained in elegant differential equations. Planck himself contributed to this resistance. He did not aggressively defend the physical reality of quanta. Instead, he presented his work cautiously, emphasizing its usefulness rather than its implications. This restraint reinforced the belief that quantization was a temporary fix, a clever trick that would eventually be replaced by a deeper classical explanation. If even its creator hesitated to fully endorse it, why should others rush to embrace it? Senior physicists of the era often viewed the new idea with suspicion. Many had built their careers on classical principles and were reluctant to accept a concept that threatened the foundations of their work. The success of classical physics had not only explained nature, but shaped professional identities. Admitting that its assumptions were incomplete felt like intellectual betrayal rather than progress. There was also a generational divide. Younger physicists were more open to unconventional ideas, while established figures tended to defend the existing framework. However, even among the younger generation, acceptance was slow. Quantization contradicted intuition, and intuition had been a reliable guide for centuries. It was not obvious how a universe governed by discrete jumps could produce the smooth, predictable behavior observed at large scales. The resistance was not purely emotional, it was also scientific. Planck's assumption lacked a clear physical model. There was no picture of what a quantum looked like, how it moved, or why it existed. Classical physics excelled at visualization. Particles traveled along paths, waves spread through space. Quantization offered no such imagery. It introduced rules without mechanisms, numbers without pictures. This abstractness made it difficult to accept as a description of reality. For several years, Planck's constant remained an isolated parameter, appearing in one specific context without clear relevance elsewhere. Without broader application, it was easy to believe that quantization was a special case rather than a universal principle. The scientific community tends to reward ideas that unify phenomena, and at first, Planck's idea seemed confined rather than expansive. The turning point came not through argument, but through evidence. When Albert Einstein applied Planck's idea to the photoelectric effect, he treated quantization as real rather than formal. He proposed that light itself behaved as if it were composed of discrete energy packets. This explanation accounted perfectly for experimental results that classical wave theory could not explain. Suddenly, quantization was not limited to blackbody radiation, it explained an entirely different phenomenon. This success forced physicists to reconsider their skepticism. The same constant that Planck had introduced reluctantly now appeared in a new context, governing how light interacted with matter. The coincidence was too strong to ignore. What seemed like an artificial restriction now looked like a universal rule. Even so, acceptance remained gradual. Many physicists accepted the results without accepting the interpretation. They used quantum formulas while avoiding philosophical commitments. This pragmatic approach allowed progress without forcing immediate conceptual surrender. Over time, however, repeated success made resistance increasingly difficult to justify. The shock to science was not a single moment of realization, but a slow accumulation of undeniable facts. Each new experiment that confirmed quantized behavior chipped away at classical certainty. Each successful prediction reinforced the idea that nature was not obligated to obey human intuition. What made the shock profound was not merely that old ideas were wrong, but that they were limited. Classical physics was revealed as a powerful approximation rather than a complete description. This realization altered the culture of physics. Confidence gave way to caution. Certainty was replaced by openness to fundamentally new concepts. The resistance to Planck's idea also illustrates an important lesson about scientific change. Revolutionary ideas rarely arrive fully formed or immediately accepted. They often appear first as technical solutions, tolerated rather than celebrated. Only later, as their implications spread, do they reveal their true significance. In time, what once seemed shocking became foundational. Planck's constant joined the ranks of universal constants, defining the scale at which quantum effects dominate. Quantization became not an exception, but the rule. The initial resistance faded, replaced by a new generation of physicists who had never known a world without quanta. Yet the memory of that resistance remains important. It reminds us that science advances not just through discovery, but through the willingness to let go of deeply held assumptions. The shock delivered by Planck's idea was not merely intellectual, it was cultural, philosophical, and deeply human. The acceptance of quantization marked a turning point in how science understood its own limits. It showed that even the most successful theories can be provisional, valid only within certain boundaries. Nature, not tradition, has the final word. What began as skepticism ultimately strengthened physics. By confronting and overcoming resistance, the scientific community expanded its understanding of reality. The shock of Planck's idea did not destroy science, it renewed it, opening the door to a deeper, more accurate description of the universe that continues to shape our world today. As the implications of Planck's idea spread beyond the narrow problem of thermal radiation, it became clear that something far larger than a single solution had entered physics. What initially appeared as a technical adjustment began to act like a thread connecting previously unrelated phenomena. The assumption of quantized energy, once treated with caution, started to reveal a hidden coherence underlying the behavior of matter and light. One of the most significant consequences of Planck's work was the realization that his constant represented a universal boundary. It defined a scale at which classical descriptions failed and quantum behavior emerged. This constant was not tied to any particular substance or force, it appeared everywhere quantization played a role. Its universality suggested that Planck had uncovered a fundamental feature of nature rather than a special case solution. As physicists explored atomic structure, the relevance of Planck's idea became impossible to ignore. The stability of atoms, which classical physics could not explain, found a natural explanation once energy levels were assumed to be discrete. Electrons no longer spiraled into the nucleus because only certain energy states were allowed. Transitions between these states occurred through the absorption or emission of quanta, producing the characteristic spectral lines observed in experiments. This insight transformed atomic physics. What had once been a collection of puzzling observations suddenly formed a coherent picture. Spectral lines were no longer mysterious, they were signatures of quantized transitions. Each line corresponded to a precise energy difference governed by the same constant Planck had introduced. The quantum was revealing itself as a unifying principle. The reach of Planck's idea extended further still. The interaction between light and matter, long debated as either wave-like or particle-like, acquired a new interpretation. Light could behave as a wave when propagating through space, but as discrete packets when exchanging energy with matter. This dual behavior, while deeply counterintuitive, accounted for experimental results that neither waves nor particles alone could explain. What emerged was a new framework in which classical concepts were no longer absolute. Instead of continuous trajectories and smooth exchanges, nature operated through probabilities and discrete events. This shift did not occur all at once. It unfolded gradually as each successful application reinforced the credibility of quantization. Planck's idea also reshaped the philosophy of measurement. In classical physics, measurements could, in principle, be made with unlimited precision. In the emerging quantum framework, limits appeared. The presence of Planck's constant implied that certain quantities could not be defined or measured independently with arbitrary accuracy. This was not a flaw in instrumentation, but a fundamental property of nature. The realization that limits were built into reality itself marked a profound departure from classical thinking. Physics was no longer about uncovering an infinitely precise clockwork universe. It became a discipline concerned with probabilities, constraints, and fundamental boundaries. The goal shifted from predicting exact outcomes to understanding statistical patterns. These developments paved the way for a deeper theoretical revolution. As quantization was extended and refined, it became clear that a new mathematical language was required. Classical equations based on continuous variables could not fully capture the behavior observed at microscopic scales. New formalisms emerged, each rooted in the same foundational insight that Planck had introduced. The impact of this shift extended beyond physics into technology and society. Devices that rely on quantum principles began to appear, even before the theory was fully understood. The control of electrons in solids, the emission of light from atoms, and the manipulation of energy at small scales became practical realities. Planck's constant, once an abstract number, became a tool for engineering. What is striking is how little of this future Planck could have foreseen. His original aim was modest, to fit experimental data. Yet the principle he introduced proved fertile beyond measure. It showed that the deepest truths of nature can emerge from efforts to resolve specific problems, not from grand philosophical ambitions. The foundation laid by Planck's idea reshaped the trajectory of science. It encouraged physicists to question assumptions once considered untouchable. It demonstrated that limits and discreteness, far from being signs of imperfection, could be clues to deeper order. Over time, quantization became inseparable from modern physics. It influenced how scientists thought about space, time, energy, and matter. The universe was no longer a smooth continuum, but a structured reality governed by fundamental units and constraints. This transformation did not render classical physics obsolete. Instead, it clarified its domain of validity. Classical laws remained extraordinarily useful at large scales where quantum effects average out. But at the microscopic level, a different set of rules applied, rooted in the constant Planck had introduced. The true legacy of Planck's work lies in this layered understanding of reality. It revealed that nature cannot be fully captured by a single framework. Different descriptions apply at different scales, each with its own assumptions and limitations. By laying the foundation for quantum theory, Planck changed not only what physics studies, but how it studies it. The discipline became more cautious, more empirical, and more open to counterintuitive ideas. The universe was revealed to be richer and stranger than classical thought had allowed. The journey from a desperate assumption to a foundational principle illustrates the unpredictable nature of scientific progress. Planck did not set out to transform physics, yet his work became the cornerstone of one of the most profound revolutions in human understanding. The framework that emerged from his idea continues to shape science, technology, and our view of reality more than a century later. The true measure of Planck's discovery is not found only in equations or experiments, but in the vast landscape of ideas and technologies that emerged from it. What began as a cautious attempt to solve a narrow problem evolved into the foundation upon which modern physics was built. The concept of elementary quanta did not remain confined to theoretical debates. It reshaped how humanity understands the universe and how it interacts with it. As quantum theory matured, it became the backbone of 20th century physics. The principles that grew from Planck's constant explained the structure of atoms, the behavior of electrons, and the nature of chemical bonds. Without quantization, the periodic table would be an unsolved mystery, and chemistry would lack its theoretical foundation. The rules governing how atoms combine, react, and transform all trace back to the idea that energy levels are discrete. The influence extended far beyond atomic theory. Solid-state physics, which describes how electrons behave in materials, relies entirely on quantum principles. The distinction between conductors, insulators, and semiconductors emerges from quantized energy bands. This understanding made possible the development of transistors, the fundamental building blocks of modern electronics. Every computer, smartphone, and digital device operates because energy and charge follow the rules first hinted at by Planck. Light itself was reimagined through the quantum lens. Lasers, once the stuff of science fiction, became practical technologies based on controlled quantum transitions. These devices now underpin communications, medicine, manufacturing, and research. From fiber optic networks to eye surgery, the applications of quantized energy permeate daily life in ways few people recognize. Medical imaging provides another powerful example. Technologies such as MRI scanners and PET imaging rely on quantum behavior at the level of nuclei and particles. The ability to visualize the interior of the human body with extraordinary precision is a direct consequence of understanding how energy levels and transitions operate at microscopic scales. Planck's constant quietly governs these processes, ensuring their reliability and effectiveness. Beyond technology, Planck's legacy transformed scientific philosophy. The certainty that once characterized physics gave way to a more nuanced understanding of knowledge. Quantum theory revealed that uncertainty is not a limitation of human measurement alone, but a feature of reality itself. This insight altered how scientists think about prediction, causality, and explanation. Nature, it turned out, does not always provide definite answers, only probabilities. This philosophical shift influenced other disciplines as well. Ideas of determinism and predictability were re-examined in fields ranging from chemistry to biology and even philosophy. The quantum framework challenged the notion that the universe operates like a perfectly predictable machine. Instead, it suggested a reality where chance and structure coexist, governed by precise mathematical rules, yet resistant to complete certainty. Planck's discovery also reshaped the culture of science. It demonstrated that foundational breakthroughs can arise from humility rather than confidence. Planck did not claim to have uncovered a new worldview. He followed evidence despite his discomfort with the conclusions. This example reinforced a core scientific value: allegiance to observation over belief. The willingness to accept uncomfortable truths became a defining feature of modern scientific inquiry. The ripple effects of this mindset continue today. Contemporary research in quantum computing, quantum cryptography, and quantum materials builds directly on Planck's foundation. Quantum computers exploit superposition and quantized states to perform calculations beyond the reach of classical machines. Quantum communication promises unprecedented security based on the fundamental laws of physics. These emerging technologies represent not the end, but the continuation of a revolution that began with a single assumption about energy. Even our understanding of the universe at the largest scales bears the imprint of Planck's work. Cosmology relies on quantum principles to describe the early universe, the behavior of radiation, and the origin of structure. The cosmic background radiation, a remnant of the universe's earliest moments, is understood through the same laws that govern blackbody radiation. Planck's constant links the smallest scales to the largest, unifying the study of the cosmos. What makes this legacy remarkable is its longevity. More than a century after Planck introduced his idea, it remains central to scientific thought. Few discoveries maintain such relevance across generations. The constant he introduced has not been replaced or revised. It has only gained deeper meaning as theories have evolved. The discovery that shocked science ultimately reshaped civilization. It altered how humans generate energy, communicate information, diagnose disease, and explore the universe. Yet its origin was humble, a physicist seeking to explain a stubborn set of experimental data. This contrast between modest beginnings and monumental consequences captures the essence of scientific progress. Planck's story also serves as a reminder that revolutions are often invisible at first. They do not always arrive with dramatic proclamations or immediate consensus. Sometimes they begin quietly, embedded in equations, waiting for their implications to unfold. The shock to science was not a single moment, but a gradual awakening to a deeper reality. In the end, the discovery of elementary quanta did more than solve a problem. It changed the questions science asks and the answers it considers acceptable. It revealed that nature is both constrained and creative, governed by limits that give rise to complexity and order. The foundation laid by Planck continues to support the expanding structure of modern knowledge. Every advancement in quantum science traces its lineage back to that first reluctant step. The universe revealed through quantum theory is not simpler than the classical one, but richer, layered, and more subtle. This enduring impact is the true measure of Planck's achievement. His discovery did not merely shock science, it transformed it, providing a new lens through which reality itself is understood. And as science continues to explore the depths of the quantum world, it does so guided by the constant and the insight that Max Planck introduced, forever altering humanity's relationship with the universe.